In this last chapter for our class, we're going to talk briefly about nuclear chemistry. So up above you can see a diagram of three different types of radioactive decay. We have alpha particles, beta particles, and gamma rays. So we'll get into all of that, and then later on we'll talk about some applications of nuclear chemistry. But first, we have to review isotopes. It's been a while since we've talked about isotopes. So recall that we can identify isotopes using the following notation. So here we have a carbon atom, and on the top left, we have the mass number. And remember, the mass number is equal to the number of protons plus the number of neutrons. And then on the bottom left, we have the atomic number. And this is only equal to the number of protons. Now remember, in general, isotopes are going to be the same element with the same number of protons, but a different number of neutrons. So for carbon, the isotope we're showing here is carbon-12, but we also have carbon-13 and carbon-14. And again, they have the same number of protons, so the same atomic number. We're just adding a neutron each time. So the mass number increases. All right, so we'll come back to isotopes in a bit, but let's talk about radioactivity. So this is really what nuclear chemistry involves. So in the 1800s, it was presumed that the nucleus of an atom didn't change, it just stayed the same. But in 1896, a French scientist named Henri Becquerel found that if uranium was placed near a photographic plate, it actually produced an image on the photographic plate. And this was really like beyond what they expected. Because, for example, let's say you just put a normal pencil on a photographic plate. You wouldn't really expect anything to happen. But in this case, even though the uranium was covered with a cloth, it still produced an image through the cloth. So there had to be some kind of radiation coming from the uranium, and the radiation was able to pass through the cloth. So they ultimately called this radioactivity. And you can see the plate here on the side. You can see where the uranium was. So further investigation showed that radiation was a combination of particles and electromagnetic rays. And the ultimate source of these particles and rays was the atomic nucleus. So there are three main forms of radioactive emissions, which we saw on the first slide. We have alpha particles, beta particles, and gamma rays. So they're just named after the first three letters in the Greek alphabet: alpha, beta, and gamma. So let's start with alpha particles. So an alpha particle is composed of 2 protons and 2 neutrons. So an element that has 2 protons and 2 neutrons is helium. So this is the same as a helium nucleus, and we actually give it the symbol He for helium. And again, the mass number is 4 because we have 2 protons and 2 neutrons. And then the atomic number is 2 because that is the number of protons. Now, sometimes you can write this as just an alpha symbol instead of the helium symbol, and then you can still show the mass number and the atomic number. So sometimes you'll see it written that way. Now, beta particles are the second major type of radioactive emission. And beta particles are equivalent to electrons. So we represent a beta particle as E for electron. And then remember, electrons don't have a lot of mass. Their mass is essentially 0. So here we're going to write the mass number as 0. Now down below we have a -1. Now the reason for that is when a beta particle is emitted, we actually find that a neutron in the nucleus is converted into a proton. So we're actually going to see the absence of a proton in a beta particle, if that makes sense. We'll talk more about this later if it doesn't quite make sense yet. And then gamma particles, actually these aren't particles, these are rays. So this is the third major type of radioactive emission, and it's really just an energetic form of electromagnetic radiation. So you might remember the electromagnetic spectrum, and it's full of different types of waves with different energies. So on the low energy side, you have things like microwaves. So those are super low in energy, nothing to really worry about. Sort of in the middle, you have visible light, so all the colors of the rainbow. And then beyond visible light, we have things like UV rays, which are what cause sunburns. And then we have X-rays, which can be used in medicine. But typically you only want to use an X-ray for a very brief, like millisecond, right? Because you don't want to have prolonged exposure to X-rays since they are very energetic. And at the very, very end of the electromagnetic spectrum are gamma rays, which are the highest energy ray. So these can do some damage, right? In fact, gamma rays can knock electrons out of atoms. And so sometimes they're called ionizing radiation, because if they can knock an electron off of something, that something becomes charged, or it becomes an ion. So this brings us back to our first slide, where I was showing the different types of radiation. And we have alpha particles, beta particles, and gamma rays. So we just saw that alpha particles are actually relatively heavy compared to the other two. So this has more mass. So an alpha particle can actually be stopped pretty easily by something as thin as a sheet of paper. Beta particles, however, remember, those were essentially electrons, and electrons don't have any mass. So a piece of paper isn't going to stop a beta particle. We need something a little bit thicker, like this piece of lead. Now, gamma rays, we didn't even talk about mass with gamma rays, and they're just a form of energy, essentially. So these have to be stopped by something really thick, so a much thicker piece of lead, for example. So when we have areas with radioactive compounds and we need somewhere to store them, we have to use something with really thick walls, something that has really thick concrete or lead that can prevent any emissions from escaping. But we'll talk more about that later. All right, so let's look at an example of the emission of an alpha particle. So earlier we said that radioactivity was discovered using a piece of uranium. So let's use uranium as our example. Specifically, we're looking at uranium-235. So again, 235 is the mass number. And then we also have the atomic number, 92. So uranium is number 92 on the periodic table. Now, when an alpha particle is emitted from uranium, we're going to lose 2 protons and 2 neutrons. And then whatever's left over will have 2 fewer protons and 2 fewer neutrons than uranium. So notice that everything is adding up on both sides. So the atomic numbers that are listed, 90 plus 2 adds up to 92, which is what we originally had. And the mass numbers add up. So 231 plus 4 is equal to 235, which is what we originally had for the mass number of uranium. However, notice that we don't end up with a different type of uranium. We end up with an entirely new element at the end of this reaction because we lost 2 protons. And now we only have 90 protons. So if we look up number 90 on the periodic table, that is the element thorium, Th. So how do we know that a product of the reaction is thorium? So again, we're using the law of conservation of matter, which says that matter cannot be created or destroyed. So we have to have the same number of protons and neutrons on both sides of the chemical equation. So this is really similar to when we balanced equations to make sure we had the same number of elements on each side. But for radioactive or nuclear reactions, we have to make sure the number of protons and neutrons are the same on both sides of the arrow. All right. Now, there are a couple of other terms that we can use here to describe the reactants and products. So chemists will often use the names parent isotope and daughter isotope to represent the original atom and the product. So again, in this case, uranium was the parent isotope. And then, of course, we emitted our alpha particle. And then thorium is the daughter isotope. So another term here that we're going to learn is radioactive decay. So when one element changes into another element through emission of a particle, it's called radioactive decay. So essentially uranium is decaying into thorium. So let's practice. Let's write the nuclear equation that represents the radioactive decay of radon-222 by alpha particle emission. And then we'll identify the daughter isotope. So we'll kind of do this one together. So radon has the symbol Rn. Now, we're probably going to need our periodic table to figure out what the atomic number is for radon. So let's see, radon is actually in the very last column on the right. So it's part of the noble gases. And if we go towards the bottom of the noble gas column, radon is number 86. So that's the atomic number. So we'll write that on the bottom left. And then we were already told the mass number. It's 222. So when radon emits an alpha particle, remember an alpha particle has a mass of 4. It has 2 protons. And now we need to figure out what the daughter isotope is. So if radon loses 2 protons, let's see, that would end up leaving us with only 84 protons. So we're forming an entirely new element here because remember, the number of protons defines the element. So which element is number 84? So you can pause the video if you want to look at your periodic table and find number 84. So it should be polonium. So let's just write that down. The element with an atomic number of 84 is polonium. PO. Okay, so now the next thing we need to do is make sure the mass numbers add up on both sides. So radon lost a total mass of 4. So what would polonium's mass be in order for everything to add up? So it should be, let's see, it would be, oh, whoops, I erased too much, 84. So it should be 222 minus 4, which is 218. So that would be our daughter isotope, polonium-218. So not too bad, right? We just have to make sure everything adds up on both sides of the arrow. It's also really cool that we can just create a new element from our original element. All right, now let's just look at an example of the emission of a beta particle. So in this case, the overall mass number is going to stay the same because remember, a beta particle is an electron, which has 0 mass. So the mass won't change. However, the quote-unquote atomic number of the electron is -1. And that's due to the fact that the number of protons increases by 1 when we emit a beta particle. So the atomic number is going to go up by 1 as a result. So as an example, the isotope carbon-14, I don't want to write another arrow there, but carbon-14, if it emits a beta particle, again, the mass number will stay the same, so 14 will remain 14, but we want everything to add up on both sides here. So our new atomic number is 7, because 7 minus 1 is 6, and that's our original atomic number. So again, in beta decay, one of carbon-14's neutrons turned into a proton, and we emitted an electron. So kind of an interesting reaction, right? Feels like it's made up, but there's a lot of studies that show this is what happens. Now, emission of gamma rays. So when radon-222 decays, both alpha and gamma radiation are emitted. So earlier we only looked at the emission of the alpha particle, but we also end up emitting some energy in the form of a gamma ray. So this gamma ray has an energy value equal to 8.2 times 10 to the negative 14th joules per nucleus. So that might not seem like a lot of energy. It's 10 to the negative 14th, which is really, really small. But if we had even just 1 mole of radon atoms that decayed, the gamma ray energy would add up to 49 million kilojoules. Because remember, 1 mole is equal to 6.022 times 10 to the 23rd atoms. So if we multiply 8.2 times 10 to the negative 14th by that number, that should give us a huge amount of energy. So that's a lot of energy. All right, so let's practice. Let's write the nuclear equation that represents the radioactive decay of a different isotope, boron 12, by beta particle emission, and we'll identify the daughter isotope. Now, just a note, a gamma ray is also emitted with the beta particle. Okay, so let's do this one together as well. So let's start with boron, which has the symbol B. And what is boron's atomic number? See if you can find its atomic number. Five. So it has 5 protons. And we were already told the mass number is 12. And then we were also told that we're going to emit a beta particle. So that's an electron with 0 mass, and it's on the lower left, we have a value of -1. All right, so now we need to figure out what is left over. So remember, everything has to add up on both sides. So see if you can figure out what the daughter isotope is. So pause the video, try this on your own, and then we'll go over it together. All right. So remember, the mass number is not going to change in this case because the beta particle doesn't have any mass. So we're not losing any mass in this process. So that'll be 12. However, we do have a -1 on the bottom. So that means we're actually gaining a proton. So instead of 5, our atomic number will now be 6. And which element has the atomic number 6? Carbon. So this is the isotope that we saw earlier. So again, we can always double check that we did it right by adding everything up on both sides. So 0 plus 12 gives us 12, which is what we had originally. And -1 plus 6 gives us 5, which is also what we had originally. Perfect. So let's just summarize the 3 main forms of radioactive emissions. So again, we have alpha particles. You can use either the symbol alpha or the symbol for helium. And the mass number is 4. And remember, alpha particles are not going to get very far because they are so massive. So in fact, alpha particles can't even penetrate your skin because they're just too massive. I mean, the helium atom itself is pretty small, but if we're thinking about what will stop it, even a thin piece of paper will stop an alpha particle. And then beta particles had the symbol beta, or an electron, and its mass number was 0. And then beta particles can penetrate skin and some tissues. So in order to stop a beta particle, you need something a little thicker, like a piece of lead. And then gamma rays are given the symbol gamma, and they're actually made up of electromagnetic radiation. The mass number for gamma rays is 0, and gamma rays can penetrate through anything. So they can actually pass through pretty much anything that isn't really, really thick, like a big piece of lead. All right, so we'll talk more about why that's important later. In the next video, we're going to discuss something called a half-life. So I will see you then.